Since we just learned about a point or a vector, let's go slightly ahead and understand the next big idea called a line, right? It may not sound very big, but let's see how the idea transpires when we look at 2D, 3D, and high dimensional spaces. So let's look at what a 2D line is, right? Suppose if this is your x1 axis and this is your x2 axis, let's say, a line here, right? If you remember your 10th grade math or 11th grade math, we always wrote our line as y equals to mx plus c, right? If this was x, if my x1 is x, if my x2 is y, I could write my y equals to mx plus c, where m is the slope and c is the intercept on y-axis, right? This is one equation of line that we all recall and remember. There's another equation of line called ax plus by plus c equals to 0. This is called the general form of an equation of a line. And they both are equivalent. You can prove it because by just rewriting this equation slightly, I can write it as y equals to minus c by b minus a by b x, right? In such a case, what happens is this becomes your c here, right? And your m is nothing but this term here, right? So this is called the general form of general equation or the general form of a line, right? We'll stick to this notation because it's easier to interpret, and this is much more general, right? If my axes are x1 and x2, I can rewrite this equation as a times x1 plus b times x2 plus c equals to 0. Instead of using ABC, let me use a different notation, because if you want to do it in 10 dimensions, how would I write it? I'll have to use all the alphabet. If I want to use 100 dimensions, I don't have enough alphabets there. So I'll write it as, I can write as w1 x1 plus w2 x2 plus w0 equals to 0. So I made, instead of a, I'm writing w1, instead of b, I'm writing w2, instead of c, I'm writing w0, right? This is the equation of a line in 2D, right? What about 3D? Some of you might have learned 3D coordinate geometry in undergrad first year math course, or probably in some cases even undergrad second year math courses, right? For those of you who don't recall it, if I have three axes, right? If I have my axes as x1, x2, and x3, the equivalent of a line, so line is a linear surface in 2D. The equivalent idea of a line in 3D is a plane, right? And the equation of a plane, for those of you who might remember it, looks like looks like this: ax plus by plus cz plus d equals to 0. This is an equation that some of you may be familiar with because you took a math course in your undergrad first year or second year. Let's just generalize it. What this looks like is w1 x1 plus w2 x2 plus w3 x3 plus w0 equals to 0. This is the equation of a linear surface. This is the equation of a plane. This is a plane, right? This is a line. The equivalent idea of a line in 2D is plane. So line in 2D is nothing but plane in 3D. Now the immediate question is, what about n-dimensional space? What is it called? It's called something called a hyperplane. Hyperplane is basically a generalization of the concept of a line or a plane to higher dimensional space. Because if you think, line is called a linear surface because it separates your whole region with a simple linear structure like a line or a plane into two regions. One region on one side of the line, the other region on the other side of the line. Similarly, a plane can separate your 3D surface, your 3D volume into two regions, one above the plane and one below the plane, right? So the immediate question is, what is the equation of a plane in n dimensions? Suppose if I have n dimensions, what is the equation of a hyperplane? You could have easily understood that by just looking at the form of this. This is 2D, this is 3D. Now just let's extend it and see what will it be in ND. In ND it will be W0 plus W1 x1 plus W2 x2, so on and so forth. Since we have n dimensions, Wn xn equals to 0. This is the equation of an n-dimensional hyperplane. Now the immediate question we get is, this is too cumbersome to write, right? Is there a more concise way of doing it? Of course there is. We can use summation here. Summation I equals to 1 to n, wi xi equals to 0. Right? Now, is there a better way to write this still further? This is still good. This is certainly much more concise way of writing the equation of a hyperplane in a dimensional space than writing out this whole expression. There is a slightly more interesting way of doing it, which is I can write it as w0 plus, imagine if I create a vector, right, w. This vector, I'll call it w. So those of you who remember how to multiply two vectors or multiply matrices, you'll quickly recognize this. Let's assume I have w1, w2, so on and so forth, wn here. Imagine if I have x1, x2, so on and so forth, xn here. This is nothing but a vector notation. This is nothing but a vector notation. This is nothing but a summation notation, right? I'm not changing any formula here. I'm just changing the notation slightly. So what does this product look like? So when you multiply this vector with this vector, those of you who have studied basic matrices and matrix multiplication probably in your 11th grade or 12th grade, you'll easily recognize this. So this is nothing but w0 plus the first component here gets multiplied with the first component here, right? Which is nothing but w1 x1, and then you take the second component, multiply it with the second component, which is w2 x2, and so on and so forth. Take your last component, multiply it with the last component, which is wn xn equals to 0. So this is a vector notation of writing it, and we'll use this notation a lot. Immediately after this section, we'll understand what is a dot product, and we'll write this in a much more concise form using vector notation. Now this vector, since this vector, I can think of this as a vector w. I can think of this as a vector x, right? This vector x has n rows, right? It has n rows and it has only one column. This vector w has one row and it has n columns, right? So if you recall the vector, the matrix multiplication, so you can multiply 1 cross n with n cross 1 to get a 1 cross 1 matrix. So those of you who remember simple matrix multiplication will quickly understand that what we have here is nothing but a simple matrix multiplication of a row vector with a column vector, right? So this is how we represent a plane. We look at a plane or a hyperplane in n-dimensional space. We'll look at many properties of lines and planes in the next few videos. Just a while ago, we realized that the equation of a plane in any n-dimensional space is w0 plus a vector w like this, where you have w1, w2, so on and so forth, wn, multiplied by a vector like this, x1, x2, if you have n-dimensional space, xn equals to 0. So I just told you a while ago that given any vector, if I write a vector w, by default it's a column vector. If I say I have a vector w which is of n dimensions, by default the default convention is, this is just for simplicity to avoid confusion between whether a given vector is row vector or column vector. So the default notation is that I have n rows and one column. So if I write a vector x of n dimensions, I'm just writing a vector here. Okay, let me define a bunch of vectors. I've defined a vector which is of size n cross 1. Let's be very specific. I'm also defining a vector x of size n cross 1, where I have x1, x2, so on and so forth, xn. Right? Now using my w and x, which are n-dimensional column vectors, how can I write this equation a little more concisely? Right? I can write it as w0 plus w transpose x equals to 0. Let's digest this. My w0, I've just copied w0 as is. Since my w is a column vector, I need to convert it into a row vector because this is a row vector, right? And how do I convert a column vector to a row vector? I just apply the transpose part. So your w transpose is nothing but, will give you a row vector like this. And your x is a column vector, which is exactly like this. So what I have here in a clumsy format, I've just concisely written it as w0 plus W transpose X equals to 0. Of course, where my W is a column vector with W1, W2, Wn components. And similarly, my X is a column vector with X1, X2, Xn components. So if you have to write the equation of a plane, again, planes are typically written with a capital pi. Right? When you write pi here doesn't mean your 3.1415. Pi, so how do you represent an unknown value? In algebra, you write it with X, right? So planes are typically written as pi. Okay, so a plane pi in any dimensional space can be written as W0 plus W transpose X equals to 0. If your W is an n cross 1 matrix, and if your X is an n cross 1 vector or matrix or vector, then this is the equation of a plane in n-dimensional space, right? You can write pi n to denote that this is an n-dimensional plane if you choose to. Now the immediate question I have here is, all this looks beautiful, but this W0 is still hanging around here. What does it exactly mean? So let's understand what W0 actually is. So let's go to our two-dimensional geometry, because that's where we can easily understand things, and we can take whatever we learn from 2D into higher dimensional space. So we'll always learn ideas in 2D and take it into ND using linear algebra. That's the power of linear algebra. When I first learned about it, I couldn't stop thinking about how beautiful and how powerful it is. Now let's say I have two axes, x1 and x2, and I have a line like this. My equation of the line, let's assume I wrote it as y equals to mx plus c, right? Where x1 is your x, your x2 is your y. Now what is m? M is nothing but the slope of this line. M is nothing but the slope of this line, right? M is nothing but the slope of this line. And c is nothing but, c is called the y-intercept. C is this point. On y-axis, where does my line L intersect the y-axis? That is called my c. It is called the y-intercept. My c is called the y-intercept, right? And my m is nothing but the slope of my line, right? Now if I write the general equation of a line, so of a 2D line, right? So general equation of a 2D line that we saw earlier is w1 x1 plus w2 x2 plus w0 equals to 0. Now let me just rearrange the terms here, and I can write it as x2 equals to minus w0 by w2 minus w1 by w2 x1, right? Now what's happening here? This is nothing but my c, right? This is nothing but my c. This is nothing but my y, right? And this part is nothing but my m, and my x1 is nothing but x, right? Now, if a line is passing through origin, okay? So if this line L, if line is passing through origin, if it's passing through origin, what happens to C? C becomes 0, right? Because this line would have, so imagine we had a line which was passing through origin. What is its y-intercept? 0, right? Let's assume I have a line L dash. If it's passing through origin, the C is 0. And if C has to be 0, your W0 has to be 0, because C is nothing but minus W0 by W2. And if C is 0, if C equals to 0, that implies in my general form, in my general notation here, in my general notation or the general equation of a line, that implies that my W0 equals to 0. So what we learn from this is the general equation of a line. But if I have to write the equation of a line that is passing through origin, okay, suppose I have a line L passing through origin in 2D, okay, what will its equation be? By just making my W0 equal to 0, what will my equation remain? My equation will remain W1 x1 plus W2 x2 equals to 0. What about 3D? Same terminology. My W0 basically becomes W2 x2 plus W3 x3 equals to 0. In 3D, it becomes a plane, of course, right? This is a line, and in higher dimensions, it becomes a hyperplane, right? In the n-dimensional space, what does this become? This becomes nothing but W1 x1 plus W2 x2, so on and so forth, Wn xn equals to 0, which is nothing but W transpose X equals to 0. This is a very, very concise way of writing the equation of a line, of a plane, sorry. This is an equation of a plane. Of course, this plane is passing through origin. This is an equation of a plane passing through origin. If it's not passing through origin, then the equation of the plane will be W transpose X plus W0 equals to 0. Okay, so this is the equation of a line not passing through origin. If it's passing through origin, it's nothing but W transpose X equals to 0. Such an elegant term. See, using the concept of a transpose, using the concept of matrix of vector multiplication, we wrote the equation of any dimensional hyperplane in a very, very concise, very, very elegant form. Of course, you have to add the W0 term if it's not passing through origin. Now let's understand the equation of a plane in a new way, using a slightly different geometric interpretation. So let's assume I have a plane pi. It's an n-dimensional plane, and this plane passes through origin, which means its equation will be W transpose X equals to 0, where W is nothing but a column vector with W1, W2, so on and so forth, Wn, and X is also a column vector corresponding to your n dimensions, right? Now, if this is the equation of plane, let's try to interpret it slightly differently. Forget about the fact that this is an equation of a plane, just for a second. Let's assume W and X are two vectors, right? We know that W dot X is nothing but W transpose X. And we know that W dot X is also can also be written as the length of W, the length of X, and cos theta, where theta is the angle between W and X, right? So here, instead of looking at W and X as part of an equation, I'm just looking at W and X as two vectors. Right? This is the beauty of linear algebra. So W is just, I can think of it as an n-dimensional point. So is X an n-dimensional point. So if these are 2 points, if W and X are 2 points in an n-dimensional space, let's assume this is W and let's assume this is X. This is the angle between them, theta, right? We said that this is equal to 0 for a plane, right? This is the equation of a plane, W transpose X equals to 0. So the moment this is equal to 0, you know that your theta, the angle between your W and X, becomes 90 degrees, right? We discussed this, right? If W is perpendicular to X, then W transpose X equals to 0, and that implies that your theta between W and X equals to 90 degrees, right? With this, let's understand a different way of interpreting this equation. Suppose I have a plane, okay? I'll write this plane as pi. Of course, I don't want to draw a 3-dimensional plane. So since a line, plane, or a hyperplane, everything is a linear surface, just for simplicity, I'll draw it like this instead of drawing a plane, because this is easy to interpret and easy to understand. Because it's a 2-dimensional surface on which I'm drawing things, drawing a line is much easier. Let's assume this is origin. We said this plane is passing through origin, right? Let's assume this is origin, okay? Let's assume this is any point x1 on this plane, right? Now, we know that W is perpendicular. So let's assume W is like this. Let's assume W is a vector like this, which is perpendicular to plane. I'll connect all the dots. Please bear with me. Now, if W is a vector which is perpendicular to your plane and at origin, let's assume W is a vector which is perpendicular to your plane pi, passing through origin, just for simplicity. Now let's assume x1 is a vector. X1 is a point, right? A point can be thought of as a vector, right? Now, since these two vectors, W and x1 are perpendicular, W dot x1 equals to 0. So for any point on this plane, if you take any point on this plane, right? If W is perpendicular to this plane, then W dot x1 equals to 0. And that's what we are calling the equation of the plane. So if instead of this x, if I replace any point on the plane, right? Instead of this x here, if I replace it with any point on the plane, then my W transpose X equals to 0, because if W is perpendicular to my plane, then W transpose Xi, so then W dot Xi equals to 0 for all Xi which belong to my plane. Let me read it in English again. If W is perpendicular to my plane pi, then W dot xi will be 0 for all xi belonging to the plane, right? This is how it's always important to read equations in English. That simplifies things for us. Now, having said that, one way to interpret this equation, one way to interpret your W transpose x equals to 0 equation is that you have a plane pi, which is passing through origin, and W is nothing but a vector which is perpendicular to your plane. Okay, this is one way of interpreting what W is. This is a very simple and elegant interpretation of W, because till now we didn't explain what W is geometrically. We just derived this W from your ax plus by plus c equals to 0 type of equation in 2D. But we never said what does W actually mean geometrically. So what W means geometrically is nothing but it's a vector which is perpendicular to this plane at origin. That's important. Okay. So one thing that people often represent W is, so because whether I have W or the unit vector W, what is the unit vector W? Unit vector W is nothing but W by the length of W, right? So because instead of W, let's assume I have unit vector W. Even then, my W dot any xi will be 0 for all xi belonging to my plane, right? Oftentimes, a plane pi is represented with a vector, with a unit vector W cap. Oftentimes it's just written as W. Okay, it's represented with a unit vector which is perpendicular to the plane. As long as, of course, we're assuming here fundamentally that this plane passes through origin. For simplicity, we often assume that our planes pass through origin, just for generality. Because in coordinate geometry, we know that I can, so for example, let's assume my line doesn't pass through origin. Okay, I can change my axis, right? I can change my axis slightly. I can shift my axis slightly and make it pass through origin, right? I'll keep my y-axis as is. I can just shift my x1 axis slightly up, right? This is called shifting of the axis and make it pass through origin. So just for generality and for simplicity, we'll assume that our planes typically pass through origin so that the equation form of it is much simpler to digest and interpret. So if it doesn't pass through origin, I just have to write W transpose x plus W0 equals to 0. So I'm avoiding this for simplicity. Let's assume all our planes from now on pass through origin unless I specifically say otherwise. Okay, so the geometric interpretation of your W is nothing but it's a vector which is perpendicular to your plane. So in 3D, if this was your plane, I'll just draw it for simplicity. And if this was origin, right, your plane, so your W is a vector like this, which is perpendicular to all the points, on this plane. Okay, so the same, the math just works even if you go into 2D, 3D, 4D, ND. That's the beauty of it, as I kept repeating myself.